In this video, we are going to look at one-sided limits, and we are going to talk about continuity from either the left or from the right. So the limit from the right, or right-handed limit, is the limit as x approaches the value c from values that are greater than c. And so we denote that in this way. We have our normal limit notation, except with our number there, with c, we are going to put a plus as a superscript. Okay, so the idea is we're approaching x, or we're approaching, our x value is approaching c from values that are c plus a little bit more. Okay, so it's c plus a little bit more. We're coming from the right-hand side. We can also define a left-hand limit. There, we are approaching c from values less than c. And our notation there, we have this superscript of a negative sign after our number c. So let's go through, let's look at an example, and then we'll look at a variety of other examples on our next page. But let's look at this example. We have j of x is piecewise defined to be negative 2x plus 1 for values of x that are less than 1. It is x squared minus 1 for values of x that are larger than 1. So if we were to evaluate this limit, we have a limit of j of x as x approaches 1 from the positive side. So 1 plus a little bit more, so we're getting closer to 1. But we have values that are a little bit bigger than 1, so we're approaching it from the right-hand side. When we're approaching it from the right-hand side, the piece where we have values larger than 1, that's this piece of the function right there. And so it's going to be the limit as x approaches 1 from the right of x squared minus 1. And we can do direct substitution there. And we get 0, which is great. If we approach 1 from the left, then we're looking at values that are a little bit smaller than 1. And so this is the way the function is defined when we are a little bit smaller than 1. And we can do direct substitution there. And we get negative 1. So our left-hand limit is negative 1. Our right-hand limit was 0. Our limit from the right. Left-hand limit. Great. So let's look at some more examples where we're going to evaluate some limits. Here we have the limit as x approaches 6 specifically from the left, from the negative side. So it's approaching 6 from the left. It is continuous at 6. And since it's continuous at 6, we can just plug in 6. So we get negative 3/4. That left-hand limit is negative 3/4. Great. On this next function, we have the limit as x approaches 2. Are we approaching 2 from the left or the right? So here we're approaching 2 from the right. We have values that are a little bit larger than 2. We can, if we tried direct substitution here, we'd get 0 over 0. And so let's factor out a negative from the top. If you factor out a negative from the top, you'll have negative of x minus 2. That denominator will factor into x minus 2 times x plus 2. the x minus 2's cancel. Now you might say, I thought I remembered a few videos ago you said it wasn't okay to cancel the x minus 2's. I did, but the context was a little bit different. Here we're talking about the limit as we approach 2, not the function itself. So it would not be correct for me to say that this function and this function where we've canceled out the x minus 2's are equal, because this function with the x minus 2's canceled out would not indicate that it's undefined at x equals 2, whereas this function does indicate it's undefined at x equals 2. However, the limit as we approach 2, those are equal even if we do that cancellation. So we do that cancellation, and then we can do direct substitution. We have -1 on top over 2 plus 2. So we have -1/4. Great. What about this third one? The third one I think is the trickiest. Here we have the absolute value of x minus 1 over x minus 1. This function is, when we have absolute values, an absolute value graph is piecewise defined. It's going to be x minus 1 as long as x minus 1 is positive, or 0, I suppose. It is going to be the negative of x minus 1, the opposite sign, whenever x minus 1 is smaller than 0. So that might feel a little bit, make you a little bit uncomfortable, because it looks like I've just said the absolute value is negative. That's not actually what I said. I said the absolute value is the negative of x minus 1 if x minus 1 was already negative, right? So if x minus 1 is less than 0, we have the negative of that negative value. We're just saying it has the opposite sign. And so that absolute value of x minus 1, it is piecewise defined to be x minus 1 if our value of x is greater than or equal to 1, and it's negative x plus 1 if x is less than 1. And so if we make that observation, then when we look at evaluating this limit, we're looking at a left-hand limit. We're looking at values of x that are to the left of 1. Then that top part we can replace with negative x plus 1. Or the negative of x minus 1. The x minus 1's will cancel, and we just get -1. If you were to graph this thing, the graph of this, to the left of 1, it's just a horizontal line at -1. To the right of 1, it's a horizontal line at +1. So as we approach from the left, our y value is just hanging out at -1. So as we move along this line, our y value is still hanging out at -1. If we approach from the right, our y value would be just hanging out at +1. All right, and one final example here. The limit as x approaches 4 from the right, from the positive side of f of x, where f of x is piecewise defined in this way. So the limit as x approaches 4 from the right is going to be, so if we have values that are a little bit to the right of 4, a little bit larger than 4, how is this function defined? For values of x that are greater than 4, it is defined by this. So we have square root of x, and we can substitute in directly And we get 2 as our limit. Perfect. All right, so that's a variety of examples where we can find those one-sided limits. Let's think about, we can use these ideas to think about the existence of a limit, but we will wait and we will look at that in our next video.